In this series of lectures on chemical thermodynamics, today I shall discuss most powerful, though not so fundamental, derived one, the Gibbs free energy denoted by G according to the honor of the scientist William Gibbs. Gibbs was an American scientist. Actually, he did not get any much honor during his lifetime, but after his formulation of this phase rule, which is the extension of this thermodynamics, he became very popular after some time. According to him, this free energy, Gibbs free energy, G definition is equal to H minus Ts. H minus Ts. H, Ts, these are all the thermodynamical properties of this system, and they are the state functions. So G is also a state function and perfectly differential quantity. And H is the energy term, enthalpy, total energy of the system, and Ts, product of these two, also gives this energy term. So this G is also an energy term. And not only that, S, entropy, measures the randomness of the system. When it is multiplied by T, this Ts will be equal to this energy of the system, which is a measure of this randomness, or we can say Ts, product of these two, is the energy responsible for the chaotic system of the chaotic properties, chaotic conditions of this system. So this Ts is unavailable energy for doing useful work. So this difference of these two, we can write the part of enthalpy, or you can say the total energy, part of enthalpy of the system. For doing useful work. So greater the value of G of a system, greater will be its ability to do the useful work, and this is why it is called the free energy. The amount of energy free for doing this useful work. I can also give a better concept of this, or physical significance of this G. Physical significance of G, or physical significance, or physical interpretation. Let us consider a reversible isothermal and isobaric process. Isobaric process. For the interpretation, let us consider a system is changing its state by the process which is reversible, temperature is constant, pressure is also constant. So this equation G is equal to, instead of H we can write U plus PV. U the internal energy and PV the pressure volume of this system, minus Ts. If we take this difference of these properties in two states, then it will be del G equal to del U plus P is constant. So P del V minus T constant, T del S. If we consider these two states, here it is the initial state of the system. The free energy, Gibbs free energy is G1, and it is the final state of the system, and it is G2. So this del G equal to the difference of these two, and del U, the intermediate change of these two states of the system, and del V, the free volume change, difference of volume of these two states, and this is the delta S, the difference of this entropy of these two states. So we know by combining the first law and second law, I have shown in my last lecture this T del S plus W, it is the amount of reversible heat given to the system, work is given to the system, and this is equal to del U. This is the reversible heat given to the system, or the heat supplied to the system in a reversible fashion. This is the work done on the system, and sum of the two will increase this internal energy of the system. So instead of del U, instead of delta U, well, I can write this one. So T delta S will cancel, and it will give you this W plus P del V. So if we consider, actually this one is the pressure volume work, or we can say also the mechanical work. So P del V is equal to minus mechanical or PV work. WPV work equal to minus P del V delta V, and so I can write here this one is the W minus W PV. So this is the total work. W is the total work. It is fully mechanical or fully non-mechanical or partly mechanical or partly non-mechanical. So from this total work done on the system, and this is the only the mechanical work subtracted, and so this one will give you this W non-PV work. Non-PV work means the non-mechanical work. So whenever this non-mechanical work is done on the system, it will increase the free energy of the system. So I can show this one. The free energy will increase whenever this work, non-PV work is done on the system. Whenever the non-PV work or this non-mechanical work is done on the system, and the system will increase this free energy. So greater the amount of work, non-mechanical work is added to the system, this work remains as energy and stored within the system. Had the value of G, greater will be the value of the non-mechanical or non-mechanical work. So whenever it comes to this state, whenever the free energy falls from the higher state to the lower state, it will produce the non-mechanical work, or W non-PV. So this is a very simple and very significant interpretation of this free energy change. Here the value of this free energy of the system, greater will be its ability for doing this non-mechanical work or non-PV work. So I can give you one example for this system. Suppose let us consider one battery or the galvanic cell. Say suppose the lead storage cell of having this 12 volt, and this is fully charged. And this one is connected to a TV monitor. This is a TV monitor. It is fully charged. This battery or this cell is fully charged means G is maximum. G maximum. Fully charged. And as this cell is used to watching this TV program, this cell is actually producing this electrical work. This electrical work is used to run this TV. So electrical work is a non-PV work. So this will be free energy will be getting decreased while we are watching this TV program by the use of this cell. So whenever that means G will be decreasing, and whenever G attains a minimum value, when the G attains a minimum value, the cell will be totally adjusted and means fully discharged. And if we again and this TV program will be totally stopped. If we again try to charge this cell, then its free energy is to be increased. And whenever free energy is to be increased, we shall have to supply this W non-PV or electrical energy is to be supplied for charging this battery to this fullest extent, and G attains again a maximum, and this cell will be ready to watch this TV. So this process is reversible, isothermal and isobaric process. So this electrical energy is supplied, and here this electrical energy is done W non-PV or I can write this electrical energy, and here also electrical energy is to be supplied. Here also the electrical energy to be supplied for charging this battery to this fullest extent. So now I like to discuss how this free energy change of a system could be calculated. So this free energy G equal to H minus Ts, or you can say U plus PV minus Ts, and also having a value of this G would be connected with this work function A, and U minus Ts A. So this will be A plus PV. A is the work function or Helmholtz free energy, and G is the Gibbs free energy, and PV is the amount of pressure volume, product of the pressure volume of the system. So if we do a reversal process or infinite change of G, a very small change of G, and all the parameters are being made fully without any sort of restriction, then it is dg equal to du plus pdv plus vdv minus tds minus sdt. But TDS plus W equal to D. And if we do only mechanical work or pressure volume work, then TDS plus minus PDV equal to del U. So if we insert instead of del U this value, then it will be this TDS minus PDV and plus VDP minus TDS minus STT. And another plus PDV plus VDP minus TDS minus STT. So PDV plus minus will cancel, TDS cancels. So dg is equal to minus SDT plus VDP. This is also one important equation. And this is also called the basic thermodynamic equation. This one is called basic thermodynamic equation. All these things I have discussed only when the process is reversible. When the process is not reversible, then actually in the former case also I have shown this del G is greater than W non-mechanical or non-PV, or greater amount of PV work to be given for the system to raise the free energy from these two definite states that I have mentioned. And this one when the process is irreversible, isothermal and isoparic in other cases. And this is also the reversal process. Now from this basic thermodynamic equation, we could give one idea how this free energy changes with this pressure, how the free energy changes with the temperature. And suppose one at a constant pressure, at a constant T, means the process is reversible, isothermal, and in that case dg equal to vdp. But if we consider this ideal gas, V equal to nRT by P. So putting here this one dg equal to nRT and here dp by P. If we do the integration, since the process is reversible, we can do this integration and this one. And it is equal to G1 and G2, here it is P1 and P2. Means the free energy G1 when the pressure is P1 of the system, G2 is the free energy whenever the pressure is P2. Air is the number of moles of this gas, T is the temperature constant, so it is taken outside of this integration. So or we can write G2 minus G1 or del G equal to ANRT and ln P2 by P1. So this equation could also be used, this expression of free energy change could be used to do this simple problem. Whenever the, say 2 moles of an ideal gas undergoes the expansion from 10 atmosphere to 1 atmosphere at a temperature of 27 degrees centigrade, free energy change for that process could be calculated by the use of this expression. And this one again I can write this G2 this equation I can write G2 minus G1 equal to ART ln P2 by P1. Let when P1 equal to 1 atmosphere, 1 atmosphere means it is the standard state of the ideal gas. Then G1 we can write G naught, and when P2 equal to P atmosphere, then G2 equal to, let it be G. So putting this here, this is G minus G naught equal to ART ln P. So this G naught is the standard. This G naught is the standard free energy of the system. Free energy of the system. So if we divide by L, you know this G, these are the extensive properties. So G by L, molar free energy, equal to G naught by L, standard molar free energy, and plus RT ln P. P is the pressure of this system when the free energy is G. So this term G by L, molar free energy, this term is very important in chemistry, and so this is why the G.N. Lewis has given a special name for this molar free energy, and this one is giving this name chemical potential. Chemical potential of the substance whenever the pressure is P, and this is defined, this is symbolized by mu. So this one will be mu, and this one equal to mu naught, standard chemical potential of the system, and plus RT ln P. Or we can write this better way. This mu is a function of a temperature pressure. Temperature pressure both can affect this value of the mu of this substance, and this one equal to mu naught. Mu naught only depends on temperature and not this pressure. Pressure is taken the 1 atmosphere. So it is only the function of T plus RT and ln P. This is also very important relation. of this chemical potential of a pure substance. For pure substance, and this means hard the pressure greater will be the chemical potential of this system. That means hard the pressure greater will be the chemical potential. We can also draw one graph. Here it is the mu Tp, and here it is the lnp. Here it is 0. ln 0 means the pressure is 1 atmosphere, and this graph will be like this, and this one is linear having the intercept. This value is mu naught and T. When this lnp equal to 0 means pressure equal to 1 atmosphere, this one equal to this. We can give a physical significance of this mu by in another way. Suppose here one container having a partition in this middle, suppose, and here the hydrogen one gas, say let it be hydrogen gas. Here also same gas, hydrogen gas, and here the chemical potential. Here the pressure is P1, here the pressure is P2, and P1 is greater than P2. P1 is greater than P2 means that this gas, this same gas is at higher pressure. This is at lower pressure, but they are separated by means of a partition. If we can make a hole of this partition, then this gas, hydrogen gas, will move from this higher pressure to lower pressure. Means instead of until the pressure becomes equilibrium. So in this case, instead of P, we can write mu. Higher the pressure means the higher the chemical potential. So mu 1 is equal to mu 2. And this process of diffusion will stop when the chemical potential becomes the same. Until the chemical potential becomes same, this process will continue. So this one is a bright example or the useful statement of the second of thermodynamics. Whenever this chemical potential of these two not equal, the process will continue, process will stop, process will occur, feasibility, and detection. In case of reactions, this substance will move from higher chemical potential to lower chemical potential. Extent of this reaction means so long this two chemical potential of these two compartment becomes equal. So actually, not only for this hydrogen gas, for any substance, the chemical potential is a measure of the escaping tendency of that substance in which it exists, and it will go to the state where the chemical potential of that substance is less. So this mu is given a physical significance, very like the entropy. Entropy measures the randomness. It measures the escaping tendency. Of the substance from the state where it exists to the state where it will go if the chances are available. So the mu actually very popular to give you the conditions of spontaneity and equilibrium. And the another form, how the chemical free energy changes with the temperature, how the chemical free energy changes with the temperature. This one is given by these relations at 2:1 at a constant at constant P, pressure is constant, means reversible and isobaric process. Reversible isobaric process. So in this case, dg equal to minus sdt. Or we can write this del G by del T at constant pressure is constant, equal to minus S. And you know, as I have stated in my last class, S is always positive. Always positive. For every substance, the entropy is always positive. So this one negative sign, so this one is a negative. Means with the rise in temperature, free energy will decrease. It is very obvious that with the rising temperature, the randomness will increase and the free energy will be less, will becomes less. Means that this system can produce the less amount of this non-mechanical work. If we do, say, by dividing by N number of moles of this gas, if we divide it, then del G by N by del T at constant pressure equal to minus S by N, and this one is the chemical potential. So del mu by del T at constant pressure equal to, and this one the molar free energy, molar entropy. This one is called molar entropy. And this one also always positive always positive. So this whenever minus included, this one, it means that with the rising temperature, chemical potential of the substance will decrease. And we know the S bar of this gas is higher than S bar, molar entropy of this liquid, and greater, and this is the solid. It means that entropy change with chemical change in chemical potential per degree rise in temperature, decrease of chemical potential per degree rise in temperature is highest for this gas and lowest for this solid. So I can give you one bright idea about this process. Say here, if we draw here temperature, and it is at constant pressure, and mu here, this has been done at constant pressure, and for this solid, the temperature coefficient of this mu will be much less, and so it will be like this. And for the case of liquid, the slope will be greater, and for the case of gas, it will be much greater. So this is the point of intersection. Here the mu of this solid is equal to mu of this liquid, means both the chemical potentials are remaining in equilibrium, and this point is actually the melting point of the substance, and here it is the solid, it is the liquid, and it is the gas. So in this case also, the mu of this liquid equal to mu of this gas, and both are equal at this point of intersection, and means liquid and vapor remains in equilibrium, and this one is the boiling point. So this is the zone of this solid, this is the liquid, and above the boiling point it is only the vapor or this the gas. So I can also define the entropy and this volume in terms of this G, as you see del G by del T, del G by del T at constant pressure from this basic equation equal to minus S, and another is del G by del P at a constant temperature is equal to V. So this is also definition of volume and entropy in terms of this free energy. And V is always positive, means with the rise in pressure, the free energy always increased. S is positive, but minus S negative, means with the rise in temperature, free energy will decrease. Here the randomness of the system is decreased, or whenever the pressure is increased at constant temperature. Here the randomness will increase with the increase of temperature at constant pressure. I can give one problem on the basis of this relation. Say, calculate the free and gives free energy change, gives free energy change when the system, when the temperature of the system is increased from 300 Kelvin to 500 Kelvin at a constant pressure, at constant P. Given S equal to 50 plus 20, 10, suppose 10 LNP. So I can utilize these relations to calculate the free energy change of this reaction for rising temperature, constant pressure. So whenever this dg, this one del G by del T at a constant pressure equal to minus S, means minus 50 plus 10 LNT. This problem is very important. This one appeared in NET CSIR PGC. So this will be the minus. This one equal to minus 50 minus 10 LNT. So this dg equal to minus 50 minus 10 LNT into dt. If we do the integration, if we do this integration here, then dg g1 to g2 equal to minus 50 integration dt t1 to t2, and here minus 10 integration ln t dt t1 to t2. If we do the integration, then here it will be del g delta g g2 minus g1 equal to minus 50, here t2 minus t1, and minus 10. Actually integration of ln t dt equal to t ln t minus t plus some constant. So here it will be written as this T2 ln T2 minus T2 and minus T1 ln T1 minus T1 bracket close and bracket close. Now I can put this T1 equal to 300 Kelvin, and it is in joule per Kelvin. This is the unit. And T2 equal to 500 Kelvin. If we put here all these terms, then I shall get this del G is equal to minus 24,250 joule. 200 300 352 joule. So these are the all about this free energy, Gibbs free energy. Again, I remind one thing is that whenever the process is reversible, isothermal, isobaric, then only this change in free energy is equal to the W non-mechanical. Whenever minus del G equal to whenever the process is not reversible, isothermal, isobaric, in this case free energy will decrease the same amount, but the work has to be given to the system greater than the case. And whenever the free energy is decreased, it is delta G, and this is the amount of work, non-mechanical work done by the system, and non-mechanical done by the system will also be less than it would be in case of reversible isothermal isobaric process. And you can see there are so many processes which are reversible isothermal isobaric. Say here any solid is changing into this liquid, phase change, solid to liquid, and this process, so long the solid and liquid remains in equilibrium, the temperature is constant, and the pressure is also constant, and the process is a reversible process. Process is reversible as there is a infinitesimal change of temperature for this solid to liquid, as from ice to water, or in case of this boiling, there occurs a phase change at constant temperature, pressure, and this process is totally reversible. So this relation, free energy, will play a very important role. This is all about the free energy, Gibbs free energy, and next lecture I will give on the Gibbs-Helmholtz equation and the Maxwell's relations. Thank you all who are watching this video, and I hope you will find it interesting, and if you find interesting, then please subscribe.